So if we get into talking about moles, I find it helpful to go back to the candy analogy and think about the fact that if you were a candy maker or you worked at a candy store, um, if you actually had to count individual candies, that would be basically impossible. If you actually had to do an inventory of all the candies that you were buying and selling, like think of, and I usually use M&Ms as the example because they're very tiny. And so even at that scale, to count M&Ms would just take you so much time, it wouldn't be practical. So what do candy makers and candy stores use instead? They actually bag up M&Ms, and that way, assuming a bag is a set size, they can assume that a bag always holds a set number of pieces of M&Ms or whatever candy, but we'll use M&Ms for this example. And assuming the bag always holds the same number of pieces, then a bag has a particular mass. Well, for now, we'll call it the bag mass. So for any given type of M&M or type of candy, rather than dealing with the individual pieces, it's going to be way easier to deal with thinking about the number of bags of M&Ms or the mass of M&Ms that I have. And that would make actually dealing with the practicalities of shipping, producing M&Ms, selling M&Ms much easier if you can use sort of a bagged up set amount. So for our analogy, we'll use the idea that a bag of M&Ms holds 600 pieces, 6 times 10 to the second, and that it weighs 500 grams. Okay? So these are some simple conversions, and obviously the idea here is the conversions that you do right now with the bags and the M&Ms are really no different than the ones that you'll end up doing with moles and atoms. So how many pieces are there in 15 bags? Well, in 15 bags, times the conversion factor, we want it per bag, there are 600 pieces. So 6.0 times 10 to the 2 pieces, and that's per one bag. So whenever I convert, I want to cancel out units. So I put bags on the bottom, and that way bags will cancel out. And so really my math is 15 times 6 times 10 to the second. 6 times 15 is 90. So that equals 90 times 10 to the second, which is 9 times 10 to the third pieces. Right, so the math is this involves a little bit of scientific notation, but it should be pretty simple multiplication and division. Okay. All right. Now a slightly more complicated question that involves two steps. How many pieces are there in 2.5 times 10 to the 6th grams, or 2.5 million grams? Okay. Well, if we set that up here, let me copy that for the sake of time. So this many grams, and then I want to get rid of grams. Grams will go on the bottom. So 2.5 grams, we're going to put grams on the bottom. And there are 500 grams in one bag. So again, the unit that I want to convert into, I always put on the top of my fraction, and the unit I want to get rid of, I put on the bottom of the fraction. So this converts into number of bags. And then if I want to just keep going and do all of my conversions at once, I can do that. I've got 600 pieces per one bag. And so now I have successfully canceled grams in the first parentheses conversion factor, and then I've canceled bags in the second conversion factor. And so I've got to do a little math here, but I can do, if I want to make this easier on myself, I would probably, because I can't use a calculator, so I'd probably make this 2,500. And by making it 2,500, I've moved the decimal over 3 spots. So that makes it times 10 to the third for the first part. And that's divided by 500. So that's going to get me 5 times 10 to the third. And then once I've got 5 times 10 to the third, now I can multiply that times that last parentheses, which is 6 times 10 to the second. Well, 5 times 6 is 30. Go back to typing here. So it's going to be 30. And then we've got 10 to the third and 10 to the second. So that's times 10 to the fifth. And if I want to do correct scientific notation, it'd be 3 times 10 to the 6th pieces. Fix my superscripts. So again, the conversions, I mean, at this point in your science career, you should have done some conversions. And if you don't have experience with conversion factors, I'll use them again repeatedly in class. But hopefully this concept doesn't seem too foreign, that if you knew the number of grams and you knew that every bag weighed 500 grams, it'd be a simple conversion to get the number of bags. And then you know the number of pieces per bag, so times that number, you get the number of pieces total. I'm gonna move on. It's the same concept if you worked backwards, just setting up conversion factors. Okay. We could also take this one step further, as the IB will when we talk about particles. And some candies are just one solid piece, but maybe we would think of another candy that's actually made of multiple different candy pieces. So again, sticking with M&Ms, now I'm looking at a peanut M&M and considering that a peanut M&M is actually made of multiple parts. It's made of one peanut, it's made of a chocolate piece, and for the sake of our analogy here, I'll say it's made of 2 thin candy shell pieces that get fused together. I'm only really showing one here, but for the sake of the analogy, go with me. We've got one peanut M&M really is made of 4 parts. So these conversions are really going to be the same. That if you know the number of bags, 20 bags times the number of pieces per bag, which is 6.0 times 10 to the second. Forgive my sloppy writing. And so then we're going to do, 20 times 6 is 120 times 10 to the second. And we could adjust to put it in proper scientific notation, 1.2 times 10 to the 4th. So it doesn't matter if it's peanut M&Ms or regular M&Ms. If every bag of candy always holds the same number of pieces, then this conversion is the same for any type of candy. 20 bags times 6 times 10 to the second is the number of pieces per bag, and you get the number of pieces total. Now, candy parts, this is where it gets slightly more complicated and really just adds one more step. If we've got the 10 bags of peanut M&Ms, the easiest thing to do is to first figure out how many M&Ms are there. So in 10 bags, we're going to have, this is being screwed, there we go, 10 bags. There are 6.0 times 10 to the second. Pieces for one bag. Let me fix that. Okay, that's the first part. That would tell me how many M&Ms there are. And that would be, 10 times 6 times 10 to the second is 6 times 10 to the third, or 6,000 pieces. Well, in every piece, there's actually 4 candy parts. So in this question said, how many total candy parts are there when you have 10 bags? Well, if you have 6,000 pieces, it's going to be that, and then we're going to have to multiply that by 4, because there are 4 parts per candy piece. Right? So that part, having some technical difficulties here. And so then we get 24 times 10 to the third, or 2.4 times 10 to the fourth. And that's candy parts. Okay, so all that it does when you have a question where your individual particle, in this case your M&M, is actually made of multiple pieces, the questions could get slightly more complicated. They could go one step further by starting you with the number of bags you have and actually asking you how many individual parts there are. So it's really just one extra conversion step. Go from bags to pieces, which we've already done a couple times now, and then go from pieces times the number of parts per piece to get the number of candy parts. Okay, so at this point, hopefully that concept is okay, and we can try more in class if you're still getting stuck on it. But where it leads us to is this unit that we're going to use in chemistry called the mole. So the way you should think of a mole is it's really just a simplification. It's sort of like the chemist's like candy bag. It's a unit that stands in for a certain number of particles. And so if you think that counting M&Ms would get obnoxious and not practical if you were a candy maker, well, counting atoms or molecules is completely impractical because they are so tiny, so much smaller even than M&Ms. So it's really useful for chemists, for scientists, if they can use a larger amount, but a set amount of particles when they're doing reactions and converting substances and the like. So a mole is 6.022 times 10 to the 23rd particles of a substance. And most of the time when we use it, it's actually just going to be 6.0 times 10 to the 23rd. We're normally going to use this number on paper 1 when we don't have a calculator. So you can normally think of this number, or known as Avogadro's number, as 6 times 10 to the 23rd, which is why in the previous examples I used 6 times 10 to the second, so that the math really looks the same. Technically, a mole is defined, it's the number of carbon-12 atoms in exactly 12 grams of carbon-12. Carbon-12 being a particular isotope of carbon that has 6 protons, 6 neutrons, and 6 electrons. So that's like the standard for this number. But anyways, it's really just like if I say I have a mole of carbon atoms, that means I have 6 times 10 to the 23rd carbon atoms. So just like a bag meant I had 600 M&Ms, whenever I have a mole of something, it means I have 6 times 10 to the 23rd of those somethings. We're also going to get actually more often using conversions between moles and mass. And so every substance, when you have a mole of it, it has a particular mass in grams that's known as its molar mass. It's different, obviously, for each substance depending on what it's made of. So to finish off, where does that number come from? Well, let's think back to the relative masses. For a long time, scientists had figured out these relative masses, especially for a lot of the elements. And so they already had periodic tables that had the relative atomic masses of elements. So like neon and radon, it was known that when you compared them to each other, neon weighed about 20 and radon weighed 222. And as science advanced, as technology advanced, and they were able to figure out much more accurately how small atoms were, then they started to ask themselves, well, we want to keep these same numbers, this 20 for neon and this 22 for radon. How many atoms would we need to get 20 grams of neon or 222 grams of radon? So notice we keep the number the same, and all that changes is instead of it being like this sort of unitless relative mass, we now have a mass that has a practical unit of grams. So as they did their calculations, what they discovered is that this turns out to be how many atoms of neon you need to get 20 grams of neon. And this also turns out to be the number of radon atoms you would need to get 222 grams of radon. It's a giant number. This is as precisely as it's known. This eighth decimal point is the estimated uncertain digit. So that means we only know the number of particles in a substance to the quintillions place. But that's not really the point at the moment. The point is that this number, known as Avogadro's number, or N sub A, is the number of particles in a mole for anything. And so the conversions that you're going to do with moles and grams are really the same as what I just did with bags and grams and pieces of candy. To go from a mole to the number of particles, you're just going to times by Avogadro's number. So the number of moles you have, if you have 1 mole times 6 times 10 to the 23rd means 6 times 10 to the 23rd particles. If you have 2 moles, you end up with this number times 2, so 12 times 10 to the 23rd particles. If you are converting backwards, if you're told the number of particles, atoms, or molecules, then you simply divide by Avogadro's number instead to return to the number of moles, that is. Grams and moles was the same as with the bags and the bag mass. For every element, every molecule, you can figure out its molar mass by looking at the periodic table. All of those atomic masses, we're now going to call them molar masses. So take the number of grams and divide it by the molar mass. Yeah, molar mass. That gets us the number of moles, or take the number of moles and times it by the molar mass. Just use big M to symbolize molar mass, times it by the molar mass, and you'll get to the mass or the grams of that substance. So it's just, if you replace the word mole here with bags, it would be identical to what I did in the beginning of this video. Very simple, simple conversions. The real trick is not getting confused and overwhelmed by the setup of the questions on paper 1. So I'm going to leave it at there, and we will do the practice examples in class.